Hello, and thank you for attending my talk. I'm going to be talking about the hybrid functionals in FLEUR. And the hybrid functionals are a type of exchange correlation functional. And if you attended Gustav's talk earlier this week about the exchange correlation functionals, you will already know some of them. On the left, you can kind of see an overview of the different types of hybrid functionals that are used in DFT. And at the very bottom, you have the very simple approximations like the LDA. And then if you go higher, you increase the accuracy of your calculation until you're at the very top, until you're in DFT heaven, where you have an exact experimental agreement. But as you go higher and higher, the computational demand also increases. And on the right, you can see that I've grouped the exchange correlation functionals into two groups. There's the semi-local exchange correlation functionals, and there's the non-local exchange correlation functionals. And they are semi-local because to get the exchange correlation potential at a certain point R, you only need to get information at this point R. So for example, for the LDA, you only need the density at R, or for the GGA, you only need the density and the gradient. And for the meta GGA, you might add the kinetic energy density. And if you then go to the non-local exchange correlation functionals, they will depend on the whole system or parts of the whole system. So for the hybrid functionals, we are also interested in the occupied wave function at different locations R prime. But there's also another reason to make these two groups. And that is that the first three, so the LDA, GGA, and the meta GGA, they have more or less the same computational demand. So there's slight differences, but if you run FLEUR, you will not be able to tell the difference, which one is faster, an LDA or a meta GGA. However, if you then go to hybrid calculations, there's a big increase in the computational demand. And I will discuss the computational demand of the hybrid calculations later in this talk. So where do these exchange correlation functionals fit in? Here you can see the typical self-consistency workflow that we have in FLEUR. We have some initial guess for the density, we set up our Kohn-Charm potential, and the Kohn-Charm potential is made up of the external potential, some Hartree potential, and the exchange correlation potential. And while we know the external potential and the Hartree potential analytically, the exchange correlation potential is always going to be some kind of approximation. And while the magnitude of the exchange correlation potential compared to the Hartree or the external potential is quite small, it's where a lot of the interesting physics happen. So what goes into the exchange correlation potential? It's mainly two parts. The exchange is due to the Pauli principle. If you have two electrons, they're fermions, they can't occupy the same position in space. And the correlation is more or less everything else. So screening, self-interaction correction, and all other effects, they kind of get put into the correlation. And with this, then we can do our usual self-consistency cycle where we set up at a Hamiltonian, diagonalize it, get the density, mix it with the previous densities until it's converged. In order to understand what we do in hybrid functionals, we have to look at Hartree-Fock calculations. So in the normal Hartree calculation, we assume that the wave function is just a product of the single particle wave functions. But this doesn't really work for fermions, because if you exchange two particles, the sign stays the same, whereas for fermions we want the sign to switch so that they don't occupy the same position in space. In Hartree-Fock, we enforce this by using the Slater determinant rather than a simple product, and then by design we have exact exchange. Now, Hartree-Fock calculations aren't perfect, and there's a reason why we don't use them very often. And this is what leads to the hybrid functionals. So in the Kohn-Charm system, we have a good correlation, but we don't have the exact exchange. In the Hartree-Fock, we have no correlation, but we have an exact exchange. And the idea for the hybrid functional is quite simple, and there's no big theory behind it. You just linearly mix some of the exact exchange with some of the Kohn-Charm exchange, and then you take the correlation from the Kohn-Charm potential. Or if you have some more complicated functional, you can mix LDA and GGA ingredients. But in the end, it's just a mixing of two different exchanges to kind of pick the best of both worlds. And while this mixing of two theories might look strange at first, it turns out it works quite well. So I collected some data from papers, and as you can see, for the lattice constant, PBE0 is about 1 magnitude more accurate compared to PBE. And HSE is also very accurate for the lattice constant. And if you look at the band gap, you will see that HSE is much better than PBE. And this is because LDAs and GGAs in general underestimate the band gap. And so you'll ask yourself, what's the cost of this nice accuracy? I guess everybody wants to run accurate calculations, but we don't want to wait forever. And here you can see, first of all, the scaling of the code. So a normal FLEUR calculation, so LDA or GGA, this is a cubic algorithm. So if we double the number of atoms, our calculations will take 8 times longer. But if you do a hybrid calculation, this turns into a 4th order code. So if you double your number of atoms, it will take 16 times longer. And this happens for each k-point. But in addition to this, you also have a problem with the k-points. So in normal FLEUR calculation, if you double the number of k-points, you need twice as long. You just run one after another. But in hybrid calculation, the integral is not just over k-points, but it's over k and q points. And so your runtime is quadratic in the number of k-points. So here I show the scaling for one iteration for a number of systems. And as you can see, our code scales quite well. So we always have a parallel efficiency somewhere close to 50%. And even for big systems with hundreds of atoms, we can still calculate them if we use enough nodes. And we put quite a lot of work into this. So in order for you to use this, you have to pay attention when you compile FLEUR. A normal FLEUR run with LDA or GGA doesn't really depend on the speed of the fast Fourier transform, because we are not a plane wave code, we have very small interstitial regions and our FFTs are very fast. But in the hybrid code, more or less 60% of the code is spent in the fast Fourier transform. And so it's very important that you don't use the built-in Fourier transform, but you link some library that has a fast Fourier transform, such as the FFTW or the MKL. Both work fine. And if you calculate large systems like the one I showed you with hundreds of atoms, where you use thousands of CPU cores, then I also recommend that you use a C compiler that is MPI enabled. And since you will use multiple nodes per k-point, you're going to have to use either ScalaPark or LPAR, both are fine. In addition to this, if you want to restart your calculation, so let's say you converge your calculation to a certain degree, and then your wall time runs out, and then you want to restart your calculation, then you're going to need to link HDF5, because the non-local potential is only stored if HDF5 is linked. And lastly, we are working on a GPU implementation. This GPU implementation is about 80% done. You can already use it, but the speed up is not perfect because some parts have not yet been put on the GPU. But if you take care of all of these steps, you can calculate systems with more than 200 atoms. So for example, if your node has 100 gigabyte, you can easily calculate 200 atoms. And if you want to go beyond that, you're going to need a little more memory per node. And now, since we don't have a hands-on section for the hybrid code, I'm going to walk you through how to set up a hybrid calculation and what to pay attention to. Okay, so first of all, we have to build FLEUR the way I just mentioned. And this is the line I use, but for each computer this line is kind of different, and you're going to have to go through the documentation to see what you need to do on your computer. But here are the things we want to see. We have a fast Fourier transform from the FFTW. We have HDF5. We have the progress threads, which is enabled if you have a C compiler that supports MPI. And we have ScalaPark. And with this we can build. Okay, once we have compiled our FLEUR, we can go to the folder with our imp file. And here I have a simple silicon input file, and all we need to do to turn this into a hybrid calculation is we add to the input line hip imp equals true, or if the input line is not there already, then we have to add it. And with this we can call impgen as we would call it normally, and I like to do inc all usually. And then we have an imp.xml file. We can have a look, and we can compare it to some imp.xml I prepared for PBE. So on the left we have a normal GGL calculation, and on the right we have the hybrid calculation I just prepared. And they're basically the same, so most of the parameters are the same, and there are only a few differences. The first difference is this line prod basis on the right here. This line describes the numerical parameters for the mixed product basis. We use a mixed product basis in the hybrid code, and these are the numerical parameters that set it up. So, for example, FFT cut is the size of the FFT grid. And a size of 1 means that this is the minimum size where we still get the exact result. If you want, you can reduce it a little, maybe to 2/3, and you might still get good results, but sometimes calculations fail because of this, and so we will leave it at 1. There are some other parameters like a maximum L, number of bands that we include in our mixed product basis, a tolerance for the orthogonality. So these are the parameters for our global mixed product basis. And the next difference we can see is actually in the k-points. So on the left you can see that we asked for a 2x2x2 grid, and we got 2 k-points after we reduced it for symmetries. On the right we also asked for a 2x2x2 grid, but in the end we get 3 k-points. And the reason is that hybrid calculation will always include the gamma point. And in this case, this means that we can do less symmetry operations, so we end up with 3 points. But because we include the gamma point, this means that the hybrid code is also very compatible with the one-year code. So if you do hybrid calculations, you can post-process this with 1 year because they use the same kind of k-point set. The next information that we added for the hybrid calculation is this NKQ pairs. This is basically the number of k and q pairs. So I told you earlier that in a normal FLEUR calculation, if we double the number of k-points, it takes twice as long, whereas in a hybrid calculation, it roughly takes 4 times as long. And this is because we integrate over pairs of k and q. So when you parallelize a normal FLEUR calculation, you're interested in the number of k-points. But in a hybrid calculation, you're actually more interested in the number of k-q pairs. So this is not an input, this will not affect the calculation, this is just information for you that helps you set up a good parallelization. And the last difference is actually down by the atom species. So here we have the atom species for silicon, and this includes now also a line prod basis. And this is specific to the muffin tin mixed product basis for silicon. So we actually have 2 L cutoffs, and we have a selection of which mixed product basis we choose. So with this, we can run our calculation. As I said before, we have 11 NQK pairs. So in my case, I will just set up 11 MPIs, and then I call FLEUR as I would normally. And now you will actually see 2 self-consistency cycles. So here, the normal PBE self-consistency cycle converges. And after PBE is converged, we actually do 1 calculation of the non-local Hartree-Fock potential. And then we repeat a convergence for PBE, so for GGA. So in the end, we have kind of nested self-consistency cycles, and at some point, both of them will converge. So here we still do a few PBE iterations to converge. So in the 7th iteration with a new non-local potential, both of them are converged, and our calculation is finished. And now we could, for example, compare the band gap of a hybrid calculation and a PBE calculation I did earlier. And as you can see, in the hybrid case, we have a band gap of about 0.09 Hartree, whereas in the PBE case, we have a band gap of 0.03 Hartree. But we have a very, very coarse K grid. So this does not say a lot, especially for a band gap. So these are the files that a FLEUR calculation would normally create, but we have an additional file called hybrid.h5. And this stores the non-local Hartree-Fock potential. So I told you that you need HDF5 to save this, and then you can use it to restart calculations, but you can also use it to do post-processing steps. So for example, if we wanted to do a DOS calculation, we need to copy the CDN file, as we would usually. Now we need, in addition to this, we need to copy the hybrid file to our DOS folder, and finally we need to copy the imp.xml to our DOS folder. And then we can go to the DOS folder, and we can turn on the DOS calculation. So we simply set DOS to true. I will not go into details because this already was done in a previous tutorial. And then we can run FLEUR, but this time we don't recalculate the non-local potential. So if you have to do the hybrid calculation on a supercomputer on many nodes, this does not mean that you have to do the post-processing with the same kind of setup. So here we can just use one core to calculate the DOS, and no Hartree-Fock calculation is done. So this is basically, these post-processing steps are equivalent to like a normal GGA iteration. And if we check our folder, you can see that we have a band.hdf, and you learned in a previous tutorial how to work with these. And if you want to do a one-year calculation, all you have to do is you have to follow the steps we showed you in the one-year tutorial, but in addition to this, you also need to copy the hybrid.h5 into the one-year folder, so that the non-local potential is present when you do the iteration. And with this, I would like to thank you for your attention, and I will open for any questions that you might have.